awake, what is the famous quantum algorithm that you know?
Well, it's probably mean sure, but it doesn't mean that I'm awake.
Actually, we had from your side, Dr. Ahmed, Shor algorithm, of course, and BB84 actually. Okay, which is famous, by the way? Is it BB84 or Shor algorithm? Shor. Why Shor? Because it is dangerous. It is threat. Okay, but this is
Everybody's talking about it.
yes, exactly. Okay, because actually the shocking effect that already caused by Shor algorithm when they developed this algorithm something like more than 30 years ago. Okay, he used actually quantum period filing. Okay, to estimate actually or defactor a very large prime number, as you of course you all know, to two large prime numbers. So it is very famous because this is one of the biggest threats and brought everyone attention. Because as mentioned previously in previous sessions, quantum cryptography is one of actually major areas that will be affected by quantum computers. Okay. We heard about Q-Day.
I'm sorry to interrupt, but can you share the screen along with the camera?
With the
People
camera.
online, I think we don't see the screen that well.
فين الكاميرا؟ We'll try, Dr. Ahmed.
Well, if it takes time, then forget about it. We'll follow up later. Excellent.
Okay, thank you. Great. Okay, it worked actually. Okay. So solve the second problem. Who heard about Q-Day?
So all security systems will be hijacked and it won't be safe anymore.
Okay, and when is the latest estimate of Q-Day? Today, actually, 20th of May, 2026, actually, it is after 3 years, 2029. So the Q-Day, actually, it is estimated by 2029, where we should have actually something like few thousand logical qubits to solve RSA in real time. Okay, but this is today. Okay, we are not sure about what will happen next week or next month or next year. So the door is closing. وممكن يقفل على صباعنا actually. On the other hand, BB84. Why BB84? Because quantum computing is not only a threat for cryptography, but it is only also advantage. Charles Bennett and Gilles Brassard, BB. This is the first part of the protocol name, BB. Developed this BB84 40 years, 1984. 40 years, more than 40 years now. And just recently, a couple of months, they awarded Turing Award. This is, as Dr. Ahmed mentioned, this is the equivalent for Nobel Prize in computer science. One question, why Shor algorithm didn't get Turing Award and Burnett and Brassard got it? Despite the fact that Shor is much more famous. Okay, because this is the real edge of quantum computer. Actually, we can actually use Heisenberg uncertainty principle and no-cloning theory to secure quantum communication in a way that was not available before. So this is a breakthrough in security using quantum. So quantum computing is not only a threat, okay, to our current cryptographic infrastructure, but also a huge enhancement in securing our communication. So this is the main point. So actually, the two sides of quantum computing regarding security, one of them actually is that we need actually to change our cryptographic algorithm, because with Shor algorithm and the more algorithms to come, okay, Current cryptography will be weak, but also on the other hand, we have great opportunity to enhance our quantum security. Imagine here that we have a bank vault, and this is where my valuable data is, okay? And I need to protect my data. So imagine that we have this triangle. I call it triangle of quantum security. What we need to do actually is put our vault inside the triangle, okay? This is a triangle of quantum security. So quantum security is not only post-quantum cryptography and the new family of cryptographic algorithms that most of you know already. This, by the way, this is the type of lock of the vault. You change the lock of the vault actually with something much more complex, such that even quantum computer actually will not be able to solve it. So this is the post-quantum cryptography. And this does not need quantum computer actually. This runs on our classical computer as it is, because this is actually where we are running every systems. Like Dr. Ahmed mentioned previously, classical computers will coexist with quantum computer. No one will replace the other. So post-quantum cryptography run on our existing hardware, like the encryptions that we are using in this online meeting. This is encrypted using HTTPS and RSA, for example. To upgrade it, actually, we'll just replace it with another version that will be post-quantum ready, but on the same classical hardware. We do not do this actually in quantum hardware. Okay, this is the first important part. Okay, and this is, by the way, most of the complexity because of migrations, like we'll see in a few slides. This is BB84 and the quantum key distribution. BB84 was the first one, of course. It was developed 1984, but there is a dozen actually of following quantum key distribution protocol, like E91 actually after maybe less than 10 years. Okay, this is actually how we protect our quantum communication using quantum physics. The theory is simple. The superposition of the qubit, okay, and uncertainty principle beside no cloning. This means that any hacker or attacker actually cannot take a copy of the qubit, okay, and store it, okay, because if it does this, actually, it would collapse quantum state. So the sender receiver will know immediately. So this is the next ultimate level of security actually that didn't exist before. So this quantum communication actually is a method, by analogy again with the bank vault, okay, is how to transfer or deliver the key or the secure code in motion. What about random number generators? In cryptography, either classical or quantum or post-quantum, you need actually random key in all cases. This is classical cryptography. How to generate this random key? You need unpredictable physical source to do it. What we are doing during the last 20 or 30 years actually is we use something called TRNG, True Random Number Generator, where we have some physical sensors to measure noise, magnetic fields, any multiple natural phenomena where you don't have any control. And you combine this unpredictable physical source and you generate your true random keys. The equivalent now is much simpler using uncertainty principle and using a dedicated photon chip to actually generate random photons. And this will be the ultimate and simplest and most efficient random key. So again, this is the most important part here. Actually, this is why we call it triangle of quantum security, because it is not only post-quantum cryptography, despite this is the most critical part, but also securing our communication with quantum communication like quantum key distribution and other protocols, and also making sure that the root of trust, I generate true random keys. Okay, and of course, all of you actually, this is not new. NIST started 10 years ago actually in highlighting this vulnerability. Okay, even 10 years actually you didn't have quantum computers in 3 or 4 5 qubits. Okay, but it was enough actually to prove the concept of Shor algorithm that was developed 30 years ago on a very short RSA key, of course. So during the last 10 years actually there were, I guess, 3 or 4 rounds till they announced the FIPS standard, I guess, last year. So the problem statement is that quantum computers are getting powerful, okay? And the Q day, this is the day when we have cryptographically relevant quantum computers. The estimate today, by the way, today, 20th of May 2026 is couple of thousand logical qubits. 2 months ago, actually, we were talking about million qubits to break RSA. So in 2 months, actually, this is one order of magnitude less, okay? And again, we're not sure what will happen next week, next month, or next year. There is a famous theorem called Motka theorem. It says if you x plus y greater than z, actually, then you have a problem. X is the migration time that you need to migrate to post-quantum cryptography from your existing cryptographic, okay? And Y actually is the shelf life of your data till when actually your data will be valuable or critical or sensitive. And Z actually is the third time. This is the day to a Q day, which is how many years from today? 3, less than 3, okay? If this was the first time actually we do this cryptographic migration? No, actually, this was happening during the last 50 years. There was many milestones where we changed or migrated different cryptographic algorithms. Okay. Now we have the new standard, but this is not the only standard that we'll see together. Okay. And we have till from here actually till Q day actually to do the migration. Why this is a little bit complex, we'll see in a few minutes. So this is not new. Migrating or upgrading my cryptographic infrastructure is nothing new. Actually, it happens almost every 10 years during the last 50 years. But now the scale or the complexity of migration is a little bit different. And we'll discuss this. So regarding standard, what everyone is doing, of course, NIST, the top active more than 10 years, different 3 rounds at least, till they reached FIPS 203, 204, 205, okay? But this is not the only standard, okay? Because actually we have parallel standard in the European Union and they are not using NIST standard. And another standard, confidential, of course, in China, okay? They develop their own proprietary cryptographic algorithms, but it is not public, of course, not open source. And you have also evolution and progression in the Middle East, in Saudi Arabia, United Arab Emirates, and Qatar, where they are started to putting their deadline for completing quantum readiness assessment and putting a plan for the migration, and even they started developing their own cryptographic version of BQCs, okay? Which is, by the way, actually, in Egypt, we have actually cryptographers in all universities, actually, is one of the very strong cryptographers worldwide. So we can do this very easily. So why this is different between from region to region and country to country and continent to continent? Because it is security, actually. So everyone actually is moving his own direction. So a complete, but this is normal, by the way. And all large organizations, especially in defense and government, use their own flavor or classical cryptographic algorithm, and the same actually applies to post-quantum cryptography. Okay, another question. Harvest now, decrypt later. Is this term familiar to anyone? Okay.
quantum computer powerful enough to decrypt it?
After 3 years.
They decrypt all the packets they collected over the past.
Exactly. This is the current threat, and this is not happening today, and will not happen actually at Q Day, which is now 2029, by the way, till now. Okay, but this is already happening during the last few years. An attacker actually take a copy of both encrypted keys, encrypted data, and store it. Okay, and will be able to encrypt it actually a couple of years later, which is now 2029. Okay. One question, and this is regarding to the hackathon actually challenge. If I am securing my communication using quantum key distribution, for example, will the attacker be able to do this? Do not answer, actually. No cloning theory. If I already was securing my communication between the sender and the receiver using quantum channel, using something like BB84 or any quantum key distribution or equivalent, will an attacker be able to get a copy of my keys, encrypted keys, without being noticed? Because no cloning theory. Imagine the qubit actually is a flipping coin. As soon as you try to measure the coin, actually it will be 1 or 0. So sender and receiver will know, okay, and cancel this message and restart again. So that's why actually this is another quantum communication is another level actually of security actually available only because or mainly because of quantum computing. Okay. What about Q Day? Q Day actually the same attacker actually will be able actually to collect the encrypted key and collect the encrypted data and decrypt it in near real time. This is what will happen. Okay, so what we need to do first, actually, I need to know what I have. What are my cryptographic algorithms that we are using? Okay, usually called the cryptographic inventory. Okay, and also do a public infrastructure health check. This is actually the central authority that I am generating the keys, the random keys or true random keys, and distribute the life cycle, the keys, and manage the life cycle of my encryption keys. This is part of the root of security, and also do some risk assessment. Risk assessment, the simple example is that our online session today encrypted using RSA, which is not quantum resistant. Okay. One question here actually is the data shared on this online session are sensitive data? Today, no, of course. But what if it is another organization using the same platform and doing some conference call discussing internal details with different level of security? In this case, will be sensitive data. So I need to migrate it actually. So this is what we mean by risk assessment. I have a vulnerable component, but what is the sensitivity or criticality of the data that are protected by this encryption layer? If it is sensitive, I should put it as a priority. If it is not, I should delay it later actually for a couple of years, even after Q Day. One of the things that each organization should do is what we call readiness or maturity assessment. Okay, we have 9 dimensions with different weights and different maturity level. Okay, the objective actually is each organization should assess the current situation. Okay, do I have a full cryptographic inventory? No, in progress, not yet. For example, planning. Okay, did I do we have risk assessment for the partial part of my cryptographic inventory? And what about the technology and the crypto agility? Okay, crypto agility, actually you'll discuss this in detail. This is actually how flexible or difficult I can change my cryptographic algorithms. If it will take time or will take just upgrade, collect, next. Migration, do I have a complete migration plan? And actually this is the critical part. And also the technology stacks that I'm using, I'm using some open source component and commercial components. Regarding commercial component, this is a major issue. Are my suppliers, software and hardware, already has both the quantum cryptographic technology or not yet? Because actually I'm tied with them. And regulatory and compliance, like a national strategy and regulation. In the previous slide, when we talked about NIST in US and talked about China, talked even about Middle East, they have already published this national quantum strategy and the regulation that mandate actually the migration to post-quantum cryptography. Couple of years now. Actually, this is being done this year in Egypt. So we have actually our AI national strategy published maybe 2-3 years now. This year actually they are finalizing our national quantum strategy. So actually we are on the right track. So this is very important, regulatory and compliance, and awareness and workforce training. Why do you think actually I bought the maximum score?
Because awareness is a key point to make ourselves
Thank you.
more.
Like our session today, actually, and all the previous sessions that's done by Alexandria Library. So this is very nice example, actually, of the awareness. Why you are here, actually, because you're already starting, not this year, last year and the previous year, actually, to be aware of quantum computing and its applications. So this is very important part. This was not the case, actually, when I started discovering quantum computing, actually, maybe 8 years ago. Okay? No one was talking about it. But 4 or 5 years, a little bit. The last 2 years, it is increasing, and you are a very good example for this. Okay, why I need to do this actually? Because I need to know the weak point to improve it and get something actually to move forward and move to the next steps. Okay, what is the landscape of quantum cryptography? I guess anyone with some cryptography background will know that we don't have one family of cryptographic algorithms, multiple families, each one has multiple flavors. So actually it is not ES, it is not RSA, it's not elliptic curve. No, it is multiple families, including also digital signature and cipher protocols and like TLS and SSL. Okay, so actually this comprehension actually will find different families with different flavors or variants of each cryptographic algorithm. So actually it is building cryptographic inventory is not a trivial or easy task. It will take some effort, like we'll see now. Okay. From previous projects, okay, a typical data center for medium or large organization will have something like 100 virtual machines or servers. Each one typically will have 20 to 50 distinct algorithms. Think actually from application layer, the proxy server, firewall, proxy server, application servers, okay, web servers, application server, middleware, okay, service bus, workflow engine, database, operating system, network layer, storage layer. All this layer from top to bottom, the 7 layers that we all know, actually has different cryptographic algorithms and different components. I need to discover this. So we are talking about typical mid to large organization actually will have hundreds of unique algorithms that I need to collect to build my cryptographic inventory, then do a risk assessment. Risk assessment, as we mentioned, actually, what is the data sensitivity or importance of the data protected by this cryptographic layer? And put the priority, because the migration will take some effort and some time. So I need actually to start with the critical first. That's why it's a risk assessment. One dimension very important actually is we don't have one tool actually to build the complete entire inventory, because we have data in motion, okay, like the traffic actually in our online call today, and data encrypted at rest, stored in disk, database, whatever data repository. So both comprehension depends on the application, the operating system, the technology itself. So usually we discover that we need to use multiple components in different layers to detect my cryptographic algorithm. The worst case scenario here is if I have during static code analysis my application, if it is custom built, okay, use the hard-coded cryptographic algorithm within part of the code. This usually part of the difficult component actually to migrate, because actually you need to refactor the code in order to migrate, which is usually difficult, not because of replacing an algorithm with another algorithm, though this is very easy, but actually to make your application crypto agile. Crypto agile means that if next year actually we have a new version of cryptographic algorithm, actually I should be able actually to do the migration without refactoring and refactoring and refactoring. So if you are lucky, actually we'll cite the software engineered clean code, okay, where every concern or separated and or cryptographic algorithm actually separated in different modules and configuration files. So just replace and rebuild it with code. But this is not the real world, of course, actually. That's why actually post-quantum cryptography is not all about cryptographic algorithms. It is about complexity of refactoring or enhancing your architecture, because this is exactly what will happen. You need actually to rectify or refactor your architecture and some of components of your code, okay, to move to the next step actually. Migrate your cryptographic algorithm and be ready for the frequent migration. Because as we mentioned, NIST was working on this PQC standard during the last 2 years on 3 rounds. The last version, FIPS 203, 204, 205, published late 2024. But maybe within a few months, actually, you'll have another version, because the people actually are active. They are developing new algorithms, discovering new vulnerabilities, so it is dynamic. So cryptographic agility is one of the important factors that we need to discover. Ideally, one of the standard format, actually, this is just a schema definition, cryptographic bill of material, CBOM, actually, commonly used during the industry, all over the industry, okay? Just guidelines, actually, how to store your inventory data, okay? And I guess we'll have some very, very high-level example. So this is very small example, of course. This is very brief example for what should my CBOM or cryptographic bill of material look like. I have a web server running this technology, encrypted using RSA and using OpenSSL 1.1, for example, and the key length, of course, it is very important, 2048, and etc. Okay, and the recommendation, of course, you all know RSA should be migrated. This is backend DPI, okay, encrypted also with RSA 256 using Java GW tokens, okay, should be planned also. This is database encrypted with ES256, which is currently, as of today actually, okay, considered post-quantum ready. But this is today actually, okay. Tell someone like Shore, for example, discover some very powerful algorithm actually to break RSA. By the way, actually, why ES128 is vulnerable? Because of Grover algorithm, the second famous search algorithm actually. It reduces the complexity of ES by much far. So this is the minimum actually today actually can be considered post-quantum, and so on. Okay. One example also related to risk assessment. For example, this is logging service. If this logging actually for performance metrics and web logs and application logs does not need does not contain any sensitive data, just performance information, I use it for monitoring, system and capacity planning. Although that it is already not post-quantum ready, I can put it lowest priority for the migration. So this is another dimension very important for planning the effort. Okay. So how we calculate our risk models, okay, or quantum risk assessment, this is the most important, second most important part. Actually, third most important part. First one, like we discussed, my readiness, the different dimensions. Am I ready? Where is the weak point? Where I should complement? Okay. Second, lot of effort actually to build my cryptographic bill of material. Okay. Third is more or less simple. Okay, but need to be done carefully. This is GRC-like actually risk assessment. Exactly. I am doing GRC for quantum. Okay, so that's why you call it quantum risk assessment. Okay, you will see actually that we have a list of different methodologies and different frameworks. Part of them actually as industry specific, like banking. Okay, but I personally prefer actually the examples that we'll use actually is not Moscow theorem that we discussed because this is binary classifier 1 or 0, x plus y less than z or greater than z. No, we use adjusted version. We call it quantum adjusted risk score. Okay, built on Moscow theorem, but it generates the risk factor from 0 to 1. Let's take an example. This is the famous Moscow theorem. X plus y should be less than z, so I am okay. Greater than z, I'm in trouble. Okay. And this is, of course, the elements that we should collect. Okay. With this different standard regulation actually mapped to the previous slide. Let's have a look, very quick look at the equations. We have x, y, and z. Okay. Now we are calculating T, S, E, and each one has weight. WT, WS, WE. Okay. T is the timeline risk. This is the common timeline risk that we've talked about, x plus y. But we converted actually to an equation to generate something between 0 and 1. So this is the first part. This is for the T. The weight of T actually will is the next slide. S is sustainability risk, low, medium, high, critical. As we discussed, our data actually today actually is not sensitive. So the risk will be low, something like 0.1. But in another organization, another type of online meetings actually can be 1 or 0.8 or 0.9. Okay. 3, exposure risk. Exposure risk, this is related to harvest now, decrypt later. Is my data exposed to the internet, public traffic? So any attacker actually can harvest or copy my data, store it, and decrypt it later, harvest now, decrypt later or not. So this is another measure. Okay, it is here binary, 0 or 1. 0 if it is protected by PQC, 1 it is vulnerable and already internet facing. Okay. For example, actually this is 0 between 0 and 1, a score, risk score. Okay, like the readiness score, but this is from risk perspective. The minimum is 0, the maximum is 1. What about the weights? There is some commonly agreed upon weights per sector. So finance, for example, the weight time 0.4, while for IoT it is 0.5, higher weight. Okay, cloud service general baseline, no. Sensitivity, of course. So we talked about S multiplied by T multiplied by E. Okay, and each one of them has the weight factor. Okay, so the total, always the total will be something between 0 and 1. So this is some example. Okay, core banking, as we expect, of course, will be critical. And on the other spectrum, actually serverless function. Serverless actually does not have just process data, that does not store anything. So actually, even it is not post-quantum ready, it does not have any data at all, actually, not even sensitive data. So actually, it will be very risk score, and I can keep it for many years, actually, till the normal migration. Again, this is a long-term plan, couple of months, maybe couple of years. So I need to take some immediate actions. Adopt a hybrid strategy. Hybrid strategy, like we'll see, actually, is that I cannot migrate everything at once. Okay, so I need to start actually with putting something like isolation layer to separate external from internal traffic, and also start with the critical assets, okay, and actually work on the organization level, because this is mainly the bottleneck or the barrier. The organization should work all the organization work in this directly, not the IT only. One quick example related to hybrid approach, okay, which we call a proxy pattern. Proxy, we all know proxy layer. Actually, I'll add just another, I replace my proxy with a BQC ready proxy, such that my external traffic always is encrypted with one of the post-quantum cryptographic algorithms, okay? So at least I mitigate the harvest now, decrypt later, till I migrate all my internal system later, maybe next month, maybe next year, okay? This is the upgrade, okay? And also, actually, in a later phase, actually, I can introduce the new advantage of quantum computing, actually, in quantum communication, for example, securing the communication between my main and backup data center, something like that. Okay. Final slide summary. Cryptographic inventory, just summarize. Cryptographic inventory risk assessment, two most important steps, and roadmap. This is the three steps actually that I should do. Then the actual migration. And the migration actually is not simple task. This is, by the way, this is why actually this is complex, not because of cryptography or post-quantum cryptography, but because it is complex migration project. So usually I will start with the inventory and risk management and the plan. This is short term, 1 to 3 months. Mid-term, start with a critical system and do pilot migration, maybe 3 to 6 weeks. And then long term, actually, I should plan, like we have seen, all the migration for all my infrastructure within the next maximum 3 years. We don't have 3 years today, actually, we have less, because today is mid-2026. Okay. This was a quick summary. Okay, any question? Okay, very important update before we go to the break. Okay, every one of the 5 teams, right? 5 teams should have uploaded their presentation and get a code to the GitHub. Okay, and and should be ready actually by downloading all the presentation on this machine, this PC. Okay, before the end of the lunch break, because we will start immediately in presentation. Each team will take something like 10 to 15 minutes. So everything should be ready, downloaded, and we should go fast just to get some time actually for the evaluation. So the lunch break for the hackathon members is not a really lunch break. It is partial lunch break. All? No. As you agree, every team has to agree actually on 1, 2, all the team, whatever. But it must be kept within 10 to 15 minutes. Any final comment, Engineer Yusuf?
Thank you very much.
Thank you again very much, Engineer Sameh, for chairing this industry academic summit. It was wonderful to listen to all the presentations. Thank you to all our speakers. And we wish, for those who are participating online, wish you were here with us. We'll see you maybe in 3 months. Thank you very much.